Hello, good evening. Alright, we got Daniel, we got Alex. Alright, people are.
Guten Abend.
Alright, I got my coffee.
How has your day been?
Hmm?
How has your day been, Professor?
Well, it's okay, we're close. It's December 1st, believe it or not. So it has been about about 9 months. A little less than 9 months, since we went online because of COVID-19. So it's kind of interesting. It's kind of interesting, how it is going to end too, because I think it's going to be a very interesting way to end this. All right, all right. So it is 7 o'clock. It's 7 p.m. So I'm gonna get started here. There's a homework assignment due tonight. That's params and return value. And there's one that is still active that is due on Thursday, which is function calls. The next one is going to be a recursive call, subroutine. Um, Next exam is going to be the final. Yes, that is correct. So for the final exam, I cannot restrict the time frame like a face-to-face class because this class is not set up as a synchronous class. So I'm gonna do the same thing like exam one and exam two, so that people can pick a time slot, on a particular day. Haven't quite decided yet on which day, um, so that is yet to be determined. And we have a text message coming in, still being typed right now. All right. So last time I gave you guys a trace, a program, and also a trace corresponding to how the stack is being used. So I hope you guys have some time to study that and to understand how the stack is utilized for just about everything except for return value. Okay, return value is not done using the stack, but everything else, okay, local variables, parameters, those are all on the stack. The return address for calling and returning, that's also on the stack. Okay, so we got some questions. Um, December 18th. All right. Yeah, so we will have a practice final exam 1 week before the final exam itself. So yes, so there will be a review. All right. So what we'll do today is, well, I got a few things on the topic that I kind of want to talk about. Several of these, one is really kind of important, but the toy processor doesn't have the mechanism of doing it yet. Okay, and that has to do with interrupts. So I can talk about the concept of interrupts, but there's no way to actually play with it because the toy processor still does not have an interrupt mechanism. So let's go with that. Okay, it's just kind of a discussion thing, and quite obviously, I cannot really ask any questions other than looking for code that would kind of use the stack in the wrong way. Okay, remember what I said? Everything that is below where the stack pointer points to is kind of subjected to gremlins, and little, you know, background, ghouls, that can kind of mess around, with this, the space that is below where the stack pointer points to. Okay, so we'll go with that, and explain why that is the case, at least in the first part of today's lecture. So one thing we can do is to kind of look up, and we can look up interrupt processor. Okay, and there are tons of if you just look at Wikipedia, I mean, this is like a mini lecture all by itself to talk about, computer or processor interrupts. So you can see, how, it relates to an operating system, because it is the operating system that is usually responsible to talk to the hardware. And the portion that talks to the hardware is the portion that needs to handle interrupts, but it really is a hardware feature. So in order to make use of interrupts, you need two things. One is you need the hardware to support it. Okay, and this is why we can't really play with it in the toy processor, because the toy processor lacks the interrupt mechanism. And I thought about adding that for a long time, but it's not going to be a very trivial addition, and so I have to do it in a very careful way not to break existing stuff. So that's number one. The second one is, even though interrupts is even if you have hardware that is capable of doing interrupts, the software also needs to make use of it. Okay, so you need both of these in order for interrupts to be useful. Okay, so let's kind of get away from the concept of interrupts from the perspective of computer architecture, and instead we'll look at a lazy professor. I'm not going to name that person, but we'll look at a lazy professor, okay, who, during office hour, especially now that we have COVID-19, would much rather be, I don't know, let's say watching Netflix, okay? Yeah. So, let's just say that, we have this certain professor, who is watching Netflix during an quote unquote scheduled office hour. And whenever a request comes in, let's say it's done by Epic, yes. So whenever a request comes in, through, let's say, Discord, okay, so there's a notification coming in through Discord, then the professor would go like, oh, really? Pause, right? Use the remote control, pause, Netflix, and then go like, okay, who has a question? Oh, I see. Somebody has a question about pointers. Fine, I'll answer the question. Okay, and the professor walks away. Answer the question, interact with the student. Using text or whatever. Okay. Oh yeah, Netflix is actually doing really well during COVID-19. Actually. So anyway, the professor would interact with the person who's asking the question until it's done, and then the professor would go like, okay, finally I can go back to Netflix and unpause, right? Continue to watch the show. That is the concept of interrupts. Yeah. So every time you want to think about interrupts, just remember that scenario, okay? Then you go like, okay, so if that is the scenario of using interrupts, then who is playing the role of the processor? Who's playing the role of the computer hardware that is attached to the processor, like the SATA controller, okay? Maybe the PCIe bus controller, and so on, okay? And what would life be like without interrupts, okay? So I'll address the last question first. Okay, once again, I'm using the stack concept, right? Last in, first out. So, what would life be like without interrupts? And in the context of this professor, okay, who would rather be watching Netflix, but still want to get the job done, during the office hour. So without interrupts, that means there's no notification mechanism. Okay, students will be lined up, having questions, but they have no mechanism to basically notify the professor and to let the professor know that they need attention. Okay, so without the mechanism of quote unquote notification, which is interrupts, the professor will now have to do polling. In other words, every 5 minutes, okay, the professor better remember to check the messages on Discord. It's like, okay, I see there's nobody, needing my attention, and then get back to watch, Netflix. So the professor will need to actively poll, P-O-L-L, poll, the status, on Discord. And polling, is not really bad from the perspective of, if there's only one thing that the professor needs to poll, it's not too bad, okay? But if there are many things that the professor needs to poll, then becomes an issue. Okay, in other words, if the professor is also trying to make spaghetti, okay, and need to check on the pot like every 2 minutes or whatever, okay, that becomes an issue, because now the professor needs to check the spaghetti every 2 minutes, check Discord every 5 minutes, right? So if the more things that the professor needs to interact with, then the more things the professor needs to add to the list of what he or she needs to check, from time to time. And that is, live without interrupts. Okay, because so now the other thing that we need to do. Okay, I just got this working like yesterday, so I'm pretty excited about it. So I got my Remarkable. You guys know about the Remarkable, but I was using the Remarkable app before, which has certain problems. Okay, I'll say it's just not very responsive. So instead of doing that, I found a hack online, because the Remarkable is actually a Linux box, well, Linux tablet. Okay, so somebody found a hack, and it was a really simple one. Just using SSH and a few other very simple commands to capture the mouse, I mean the pen movement on the tablet, and register, when the pen is actually writing something. So this is what we'll do. Okay, is for me to illustrate, what it is like with polling and without polling, and also who is a hardware device. Okay, so here's a professor. Okay, the professor has mustache. Okay, and all right, so here's the professor, and let me scroll up here a little bit. Okay, there we go. And then we have students. Okay, so we have a student here, and so the student is actually the hardware. The professor is the CPU or the processor. So normally the hardware is going to do its own thing, right? The network controller, for instance, is going to monitor the Wi-Fi signals or the Ethernet signals and whatnot, and be able to do. Most hardware can do things on their own for a while, okay? But once in a while, the hardware is going to say, "Oh, I just received something." Okay, here's a packet. Okay, I double checked, make sure it's okay. Everything seems good to me, but I have no idea whatsoever of what to do with this packet, network packet that I have just received. So in that case, the hardware is going to say, "Hey, processor, I need your attention because I just got a packet." Much like a student, having a question, while doing the homework assignment, and it will just basically notify. Okay, so when we say the word interrupt, okay, it really is the same thing as what we know as a notification on a phone. Okay, you basically hear a beep, it vibrates, zzz, and so on. Okay, it's an interrupt. Okay, it catches the attention of the processor. So then the processor, would know, oh, okay, network controller, you have, something for me. Okay, you have just received the packet. So the processor, would, so the first traffic one is the hardware interrupt, and then the processor will basically run a subroutine at that point. Okay, so the processor will now, follow a script, and this script has a very specific technical name. It is called an ISR. Okay, ISR stands for interrupt surface routine. Okay, so the processor is going to follow the script on the ISR, interrupt surface routine, and by following that script, the processor will be basically interacting with the hardware kind of a few times. Okay, so the first thing in this particular example is the processor will go like, "Hey, network controller, give me the packet that you have just received," and then the network controller goes like, "Okay, here's the packet." The processor gets all the bytes, right? uh what is the S? I'm not sure what you're talking about. Surface. Oh, bad spelling here. Surface. There we go. I transpose the I and the V. and missing the C. All right, I guess the coffee has not kicked in yet. All right, so interrupt surface routine. So the interaction is going to end at some point, right? So the interaction is going to end. So this is step 2, a whole bunch of interaction. So at the very end of this script here, okay, it's going to say the end, okay? And that's it, okay? The processor at that point can go back and watch Netflix. Unpause, the Netflix video that was paused before and keep watching it, okay? So that is the process of interrupting, okay? The advantage of interrupts is that the processor doesn't need to poll anymore. So the processor doesn't need to go like, okay, I can go through this loop 3 times, but on every third iteration, I'm gonna have to check something over there. It's like, hey, network controller, do you have anything for me? No? Okay, fine. And then the processor will continue to do whatever it needs to do. But it's really difficult to write code like that because in the middle of doing some computational intensive work, okay, you kind of have to remember to do all of the other things that can potentially happen because you have a network controller, because you have a sound card, because you have a video controller, blah 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 blah. So that list can be very, very long depending on how many things you're attaching to the processor. So using this particular method, okay, unless somebody actually has something for the processor to process, the processor can focus 100%, at doing its own processing, okay, in our analogy, watching YouTube, okay. So are we understanding this concept okay so far? Does everybody understand, how life is like with interrupts? Basically, your phone can notify you when you got a text, as opposed to life without interrupts, which is your phone not having the ability to notify you. I mean, just kind of imagine, right? Just imagine life without notification of any kind from your phone. You don't get a text message notification. You don't get a Discord notification. You don't get a Facebook notification. None of the apps is going to send you a notification. What are you going to have to do? Keep checking the phone, right? That is what life is going to be like without interrupts. Now, because of interrupts, we can keep doing things, and then we just go like, you hear a beep, okay, or your phone buzz you, then you go like, oh, okay, now I need to check. I got a text message, okay, okay, reply, and I'm done, and then you can continue to do whatever you need to do. So are we good so far, in terms of just the concept of interrupts? I'm looking at the text area. I'm polling, by the way, I'm polling right now to see if there are any messages in the text channel. Okay. Alright, so Daniel is typing. Can you clarify again, is the processor constantly looking for an interrupt, or is it sort of forced by other processes? That is a interesting question because it depends on from which perspective. There are 2 perspectives to look at this question, in the text channel. So the first one is looking at this from the software perspective. In other words, we're looking from the perspective of a programmer, okay? So you have written your TTP-ASM program and so on and so forth, okay? Your C program, C++ programs, whatever programming language you want to use. You don't have to do anything, okay, at all to look for an interrupt because it happens, but it is not your job to anticipate that an interrupt may happen between any instructions or between any 2 statements and so on and so forth. So from the perspective of application programs, the answer is no. You don't have to look specifically for all those interrupts that can be coming in from a variety of hardware devices attached to your processor. But there's a second perspective. The second perspective is looking from the perspective of the hardware of your processor. From that perspective, the answer is yes. Okay? It's not so much that it is constantly looking for something. It's just that at the end of the execution of each instruction, there is a mechanism. Okay, there's a mechanism to see if an interrupt is raised. Is there at least one hardware device needing the attention of the processor? Okay, so the interrupt is actually implemented by at least one hardware line. Okay, one conductor or one pin of the processor that is basically labeled the interrupt line. So the interrupt line is usually is an active low signal, which means normally when there's nothing going on, it has a high voltage. When at least one device says, "Hey, I need attention here," okay, then that device would quote unquote pull the line low. Okay, so that signifies that at least one device needs attention. So the processor's hardware, not software, okay? We are not talking about software that you write. We're talking about the CPU mechanism itself. So there's a mechanism to detect that the interrupt line has gone low, and then the processor will then execute, what I have highlighted here as the ISR, and get it done. Okay, so when the processor is executing the ISR, it is no different from running any other code from the perspective of the processor. It's just that this code here contains instructions that would specifically talk to the hardware over here in order to make the hardware happy. It's like, okay, you got a packet, I'm gonna get it. Okay, so the hardware goes like, okay, you have just offloaded, a network packet from me. I'm happy now. All right, so I think Dan was still typing. I'm gonna let him finish while I take a sip of my coffee. Alright, so here's a long one. So the question or the point is, oh, alright, but then doesn't that mean it's technically kind of polling for an interrupt after each instruction? The answer is sort of yes, but it is not from the perspective of the program. That is the big distinction. In other words, the programmer, okay, doesn't need to be aware of the gazillion devices that may be attached to the processor at any time. Okay, now the hardware does. Okay, the hardware has to listen to all the hardware devices that can potentially tell the processor and go like, hey, I need attention. But the software does not, and that is the big distinction. Because because the complexity of polling is coming from the perspective of software. Okay, so I guess that answers that question. So now the question is, what is the mechanism of running the ISR? Okay, in other words, the professor is watching YouTube, right, or Netflix. Okay, that was the example. So the professor is watching Netflix. Okay, and then a notification comes in, from Discord because somebody has a question, and the professor will go like, okay, I'm gonna pause my Netflix first. So the question is, what is the equivalent mechanism in a processor of pausing that Netflix? Go do whatever needs to be done and then come back and then unpause the Netflix. That is the question. And Aiden is also correct. Okay, it is the same thing as calling a function and returning from the function. In other words, the ISR is a special kind of subroutine. Okay, this word here, routine, is actually meaning it is a subroutine. Yes, by that I mean it is like a function in C or C++. Okay, so an ISR is a special kind of function. When the processor detects that a hardware mechanism, a hardware device, is needing its attention through an interrupt, the CPU would quote unquote automatically call a subroutine. Now that call of a subroutine is not written in code anywhere. It's hard coded into the processor architecture that it will go through almost exactly the same mechanism as calling a subroutine. So we kind of have to think about, okay, what does that involve? Well, it involves saving the return address, which is equivalent to where the time mark of Netflix. Okay, so that's going to be saved. Guess where? On the stack. Okay, that's going to be saved on the stack. So the processor will go like, darn it, I have to go answer a question. And then before it goes answering the question, it will pause Netflix, jot down, exactly what time, Netflix was on at that time on the stack. Okay, and then it will go ahead and follow the instruction of the ISR, the interrupt surface routine. At the very end of the ISR, okay, the processor will go back to look at on the stack, look at the time mark that it saved earlier, so that it can resume to Netflix after that. Basically to unpause, okay, Netflix at that point. So that is why, we, from our perspective, when we are writing application software, it is not a good idea to utilize any stack space that is below where the stack pointer points to. So now is a good idea to continue to use the tablet to kind of draw another picture. Okay, so this time we're going to draw a picture of the stack. And we'll separate the stack into basically two portions. Now this is from the perspective of an application going. Okay, so let's just say from the application's perspective, the stack pointer is pointing here when an interrupt happens. So right here at this point of time, an interrupt happens. This portion of the stack is used by the application. And by mean of application, I don't really mean like Microsoft Word or Excel or something like that. It's just about any program that you normally write. Okay, that is quote unquote the application. What the ISR, what the interrupt mechanism would do is it's going to, without the software, without the application being aware of the interrupt possibly happening at any particular time, the interrupt mechanism of the processor would go through the same mechanism as calling a subroutine. So that means it's going to use up this location for a return address back to the application itself, and who knows how much more space is needed by the ISR itself. Because the ISR itself may need a whole bunch of local variables. It will have to save all the registers and then restore all the registers and so on and so forth. So who knows how many bytes are actually needed by the ISR while it executes. Okay, so this portion, okay, if I need to write this portion here, is used by the ISR. So but when the ISR is running, okay, when the ISR is running, the stack pointer actually moves all the way down to here, because the ISR, like any subroutine, would allocate stack space as needed. Okay, and it would deallocate space as needed also. Okay, so when the ISR returns, when it's done, it would basically, the last instruction is like a return. Okay, it's usually like a return, but it's a modified version of a return. It's called return from an interrupt, but it does almost exactly the same thing as the return mechanism. So after that, the stack pointer is now back to here. So from the perspective of the application program, it is as if the stack pointer has not changed, but in reality it has. So what does this have anything to do with how we use the stack? If the application, okay, so let me draw another picture here. Okay, this is the stack again, and this is where the stack pointer points to. And let's just say that the application program decides to use, I don't think anyone is going to use the next byte lower than where the stack pointer points to, and without changing the stack pointer, the the application goes like, I'm going to use up this much space. Okay, so the application program is going to use up more space than just starting with where the stack pointer points to, but also certain locations below where the stack pointer points to. When the interrupt happens, what do you think is going to happen? The first thing, when the interrupt happens, okay, this is the interrupt mechanism. So the interrupt mechanism will first overwrite this location and say, I'm going to need this for saving the return address, and therefore overwriting or clobbering the byte that the application program was using. Okay, and who knows how many more bytes it's going to use. Now, from the perspective of the stack pointer, a properly functioning return ISR would basically go, it would move the stack pointer down, and it would move the stack pointer back up to exactly the same point. So from the perspective of the application program, it would not have any idea that an interrupt had happened. But the space below, the memory space below where the stack pointer points to, is changed. So that is what happens when we try to use locations below where the stack pointer points to. And this is also why we need to decrease the stack pointer first before we overwrite that location. Because if we do the reverse, then we can end up with exactly this particular scenario, where the byte that is overwritten, in memory, is going to be overwritten by the interrupt mechanism. But there's no way for the application program itself to even know that something like this has happened, because the whole point of interrupts is it's not interrupting from the perspective of the application program itself. All right, so are there any questions? All right, so we got some questions coming in. Very good. So I think the whiteboard comes in pretty handy today. So does that mean the notification wouldn't happen then? Nope, it happened. It's just that from the applications program perspective, it's not aware of it. Okay, so I think the confusion is there are two perspectives. One perspective is the hardware perspective, from the perspective of the processor. So from the perspective of the processor, there's still polling, and the notification is understood, it is interpreted, going through all the mechanism of calling the ISR and so on. So from the hardware perspective, it is aware that something has happened, and there's also a quote-unquote polling mechanism to check that line to see whether an interrupt is outstanding or not, is waiting or not. But from the perspective of the software, okay, the code that we put into RAM, okay, from that perspective, it is completely unaware of interrupts happening. So depending on which perspective you're looking at, are you looking at this from the perspective of the program, which is the code that we put into RAM to run? From that perspective, interrupts are transparent, other than things below where the stack pointer points to can be corrupted. Okay? But from the perspective of the processor itself, it has a special mechanism to check at the fetch cycle of every single instruction execution to see whether it needs to call an ISR or not. So is that okay? Does everybody sort of understand the mechanism? It's a little bit hard to explain because the toy processor really doesn't have this mechanism, so I can just kind of talk about the concept, but I can't really illustrate it like the rest of the concepts in this class, where I can actually show you using a trace analyzer or looking into RAM and actually illustrate what it means by those concepts. Alright, so here's manual typing. And these concepts are okay. Let me first address Daniel's question. Can you use this mechanism in a virus to use someone's machine to mine Bitcoin without being noticed? And I think there are programs to do this already, except in those, most of the time, if it is legit, it would ask the user first. But yeah, but a hacker can potentially install something that can siphon processing resources. But it's not really an interrupt mechanism in that case, because based on what Daniel is typing here, um, it is running as a process. Okay, basically you are starting a separate process to use somebody else's computer to do some computation for you. So it's not really the interrupt mechanism doing this. It is a whole different process doing it. So I'm not going to get into the concept of what is an ISR, what is a thread, and what is a process. Okay, because those concepts are very much intertwined and related. If you're on the computer science track, you're going to have to take an operating system class as an upper division class in a 4-year university. In that class, okay, concepts that I have just kind of gone through a little bit, they will be hashed out, okay, big time. They will talk about what a thread is, how is a thread different from a process, and what happens with an operating system, and also what happens if you do not have an operating system. So the contrast between those two is on the Arduino, for instance. On the Arduino, there's no operating system, so there's only one single stack. Okay, unless you have your own library of code to implement threading. So there's only one stack. So that means what I have just talked about is 100% applicable. If you try to put something below where the stack pointer points to, sometimes it is there when you still need it, and sometimes it's not there when you need it, okay? Which makes those programs very, very difficult to debug, because it depends on, whether interrupts are happening, okay? And when interrupts are happening, and what kind of interrupt is happening, because, different interrupts can corrupt the stack or can use the stack in a different way. So those bugs are really, really hard to debug, okay? They're really, really hard to debug. But when you look at a Raspberry Pi, okay, a Raspberry Pi on the other hand runs Linux. So if you have Linux as an operating system, then interrupts still happens. Okay, it's still going to use a stack of some kind, but it is not going to use a user space stack. Okay, and each application program has its own stack, but the operating system, the kernel, has its own stack as well. So when interrupt happens, it's always going to use the kernel's own stack and not a user space stack. So from that perspective, okay, people can be using bad programming practice, utilize space below where the stack pointer points to, and nothing bad would quote unquote ever happen. Okay? And that basically just builds up bad programming practice, because if those programmers, for whatever reason, needs to write device drivers in an operating system and keep using the stack in this particular manner, that code is going to break. Okay, it's going to break in unpredictable way, and those are very difficult problems to resolve, because we don't even know when it's going to happen next, let alone the symptoms of when it does happen. So that's pretty much all I have to say about interrupts. It's really just the concept, but not so much the mechanism, because the toy processor does not have an basically it's called an interrupt controller inside the processor, but I don't have it implemented in the toy processor yet. So that is that. Any questions about the whole concept of interrupts? Okay, nobody. Well, let me ask, is anyone interested in writing code, low-level code for operating systems? Nobody. So nobody wants to write device drivers or low-level code for an operating system or anything like that. Okay, we got a few people. Wouldn't hurt to learn, maybe. Okay. So I'm going to use up a little bit of time to kind of talk about um, what the future holds for you guys. Okay. So when we look back in time, okay, yes, I'm old and I sometimes I look back in time because there is a back in time for me to look back at because I'm old. So back in those days, okay, back in the 80s and 90s, okay, people were mostly focused on PCs, personal computers. So we have the Apple II, and then we have the IBM PC, and then we have the Macintosh, and so on and so forth. Those are there's not a whole lot of demand of people to write device drivers because especially at the beginning of all of these computers, you don't really get to choose a whole lot of what we call peripheral cards. Basically anything that plugs into the backplane of a motherboard is called a peripheral card. These days we just call it a SATA controller and whatnot, and most of the time we don't even plug anything onto a motherboard anymore because the chipset, okay, the so-called chipset of a motherboard is already implementing most of the things that we need peripheral cards for. The sound card, the network card, the modem card, okay, most of you don't even know what a modem is, the hard drive card, and so on and so forth. All of those peripheral cards are now basically integrated into what we call the chipset. Okay, so the chipset is basically fully integrated into a process onto the motherboard. And usually, the company making the processor would also be the one kind of making the chipset, because those two need to really kind of talk in a very efficient way to get things done. So, for the most part, it's not a big deal. Okay, there are very few people who needs to understand how to write device drivers. And then comes along embedded systems, and then comes along the Arduino. Does everybody know what is the Arduino? Arduino. Nope. Oh, okay. This is really cool. Okay. So the Arduino is it's not a single circuit board. It refers to a whole family of circuit boards. Each one is, I can't even remember how much it is. So if you go to Amazon and look up Arduino, okay, you can find this is a starter kit. So it has all the other things, but does it include the actual Arduino itself? Looks that way. Looks like this is the actual Arduino. So I'm going to click this, and yep, that's the Arduino Uno. Okay, so it's basically a single board computer if you want to look at it that way. It's a very, very small single board computer that is obviously programmable. And it's actually programmable in C++ using the Arduino interface. So basically you can write fairly well, I mean it's not just simple programs. You can actually write a fair amount of code onto the processor, onto one of these single board computers. And they can interface with all kinds of stuff. Okay, if you want something simple, you can have a bunch of contact switches, a bunch of LEDs, or a bunch of transistors, controlling LEDs. So you can have your own Christmas light show if you want to, using one of these things to control the light show. Okay, and they can be networked. Okay, you can use. I think they are now Wi-Fi capable. I'm not 100% sure, but they are networkable at least. Okay, so you can now have a bunch of these things, so you can have a coordinated Christmas light show that will out Christmas all of your neighbors. Okay, that's one kind of useless application of an Arduino board. You can make a robot. Okay, because you can have these interface, these pins here. I can It's harder for me to point to something when I'm using the navigation. Okay, there we go. This is a nicer one. So when you look at these pins here, many of these pins can be connected to um, devices. They can also serve, interestingly, to match the concept that we were talking about today. They can also be interrupt lines. Okay, in other words, you can have a closure of a switch. Okay, at a door, at a window, or whatever. And most of the time, when the switch is open, okay, the Arduino would just go do whatever it needs to do, like like manning or controlling the light show that you want to do. But if an intruder comes in, through a door, a screen room, a screen door, or whatever, and it breaks the circuitry, then the interrupt happens, right? And then you can, at that point, you can catch the interrupt, so to speak. You understand that, okay, there's an event happening, and then you can turn all of your Christmas lights red and blink it. Blink the SOS, Morse code using your Christmas lights, all in red, so that all your neighbors knows that you need help. Okay? You can do that. Okay? You can do that using an Arduino board. And you can do that with fairly simplified hardware as well, because you just need a whole bunch of transistors, closure switches, and so on and so forth, and then just have to write a code to do it. All right. So what does this have anything to do with what I said? Okay, writing device drivers. In other words, how many different devices do you think can interface with an Arduino Uno? That's the next question. So there's no easy way to answer that particular question, but I can point you to a place where you can find some answers to that. SparkFun. So SparkFun is an online store. They sell a lot of stuff. Okay, so if you look at the product menu, and if you just kind of look up Arduino, okay, Arduino, it would give you a lot of stuff. So many of the products, in this search are devices they can connect an Arduino to. So many of these are actual Arduinos. So you can see there are different variations of Arduino, different form factors. But you can also see that there are different devices they can attach to an Arduino. So I think these are Shield, ETH, that's Ethernet. So you can use this is an Ethernet. This adds additional memory. There are all kinds of stuff that you can attach to. So now, going back to the question of who needs to write device drivers, how many people do you think needs to write device drivers? So as we have these single board computers that can interface with basically an endless selection of devices, the answer is we probably need more people writing device drivers. Okay. Now, if this is not enough for you and go like, yeah, but an Arduino is kind of limited of what it can do, let's look up something else. Yes, today's lecture is tech shopping. So the next one is Raspberry Pi. Okay. So how many people know what is a Pi? I do. All right. So a Raspberry Pi is quite different. Okay. So from one perspective, it is kind of like an Arduino board, from the perspective that it is a single board computer. Okay. It's a little bit bigger than an Arduino, not by much, I would say, and the price is not really too bad either. Okay, this is just a single board computer, and you can see the size of the single board of the circuit board, because you can see the top middle thing. That's a USB port, so that means this entire circuit board is not really that big. But the main difference between a Raspberry Pi versus an Arduino is a Raspberry Pi runs Linux. It does. Okay, it has 4 gigs of RAM, so it runs Linux, or a variation of Linux. Okay, it's called Raspbian, or one of the variants of Linux that can run on a Raspberry Pi is called Raspbian. Okay. From that perspective, whoever is maintaining that operating system now will basically, may need to look into what can we attach to this particular bus here. Okay, so if you look at the left hand side, you see a lot of pins, right? So those pins can also attach to additional devices, and some of those additional devices can generate interrupts. Okay, so you can have it to hook up to um, what we call an ADAC card, ADC, analog to digital converter card. So you can use it to measure things. Okay, you can measure pressure. You can, using a transducer. You can measure temperature. You can measure pH. You can measure a variety of things. But before you can use it, you need to have a driver written in Debian, in this case in Linux, so that an application program can get and process that data. Okay, so but if you think about, this is really open-ended, because somebody can invent a new device using the I2C bus or the SPI bus. Those are all serial buses that is really commonly used for something like this. So you can have a new chipset. Okay, so somebody invented a new chipset that can do accelerometer, temperature, humidity, and oxygen level, okay, sensing. But that sensor is useless unless somebody has written also the device driver on something like this, so that an application program can now utilize it to do whatever environmental control that it needs to do. So all of this, okay, is really just to illustrate to you that the landscape has changed. Okay, before we have very standardized computers with very standardized peripheral stuff that you can attach to that computer. That is no longer true. Okay, and then the second thing is, we used to look at computers and go like, oh, they can compute, right? They can do charts, they can do word processing and whatnot. Now, who knows? I mean, you can get a Raspberry Pi and do whatever you want with it. Okay, you can use it for in-vehicle entertainment system. Some people use it for that purpose, or you can use it to control a seasonal light show. You can have the same LED strings of the same string of LEDs. Okay, but depending on the season, depending on what you want to celebrate, you can control the color and also the blinking, so that you can have the same LED light string to for New Year's Day, Valentine's Day, where you display the pink color and stuff like that. Going to 4th of July, okay, where you can display white, red, and blue, right? And then we can now go to Halloween, where it can be kind of orange and black. And then we get to Thanksgiving, where it is kind of like brownish, color. Then we get to Christmas, or solstice, right? Winter solstice, where you can display mostly red and green colors, and so on. And you can attach music to all that thing too, to all that stuff, because there's an audio port to the Raspberry Pi, and because it runs Linux. Okay, it runs Linux. You can literally have a web browser like Firefox, going to a YouTube website, and then you just play the music from the YouTube clip using something like this, and then make your blinky lights synchronize with the music. You can totally do that with something like this. Now, what I have just said is a total waste of hardware like this. Okay, but there are many other useful applications of the Raspberry Pi, and there are tons. Okay, the whole point is, we don't know how many devices people would invent that can attach to a Raspberry Pi. Okay, a new device comes out, and somebody needs to write the driver for it before the operating system and then the application program can make use of it. So the whole point is, the marketplace for people who can write device driver, I think, is increasing now. Okay, and it is a very specialized kind of job. It is not the same as programming, as regular programming that you normally do. This is a little bit specialized. you don't have to always program in assembly. C actually has pragmas to turn a normal subroutine into an ISR. Okay, you just have to use the proper pragma, Pragma, to around a subroutine to basically mark a subroutine and go like, this is not a normal subroutine. This is a special subroutine that is, that's going to be an ISR, an interrupt surface routine. So it would basically, the compiler will automatically attach code to save all the registers at the beginning and restore all the registers at the end. So you can basically write your code like normal, inside the subroutine. But the important part is you have to understand the concept of an interrupt in order to write an ISR. And what I have just talked about today is the concept to write interrupt service routines. So I hope this is somewhat useful to some of you, especially those of you who like to tinker and also to work on things that is not, how should I put it, not traditional programming. Okay, it's a little bit different, and it's more challenging in many different ways. But that's also why there are not a whole lot of people who can do it. It's not like game programming, where, I hate to say it this way, where developers are more or less a dime a dozen. Okay, people who can write proper ISRs, they're not a dime a dozen. So do we have any questions about this? If anyone is interested in this stuff, I can talk more about this offline. But if nobody is particularly interested, I can move on. Okay, no one seems to be particularly interested. That's fine, not a problem. So what we'll do is we are now moving on to structures. Okay, so we'll go ahead and let me see if I can still find it right here. This is good. So we have onlinegdb.com here, and I'm gonna just define the structure and then print something, and we'll talk about it. Okay, so we'll define the structure. So does everybody know what is a struct from C? This should be a concept taught in CISP310. I'm not seeing any answers. Okay, so most people do. Alright, so I'm just going to assume most people have exposure to structures, because that really is part of the curriculum of CISP310. So I'm just going to define the structure. We'll call this, okay, XYZ, okay, because I cannot think of a particular name. So structure XYZ is a definition, okay, and now we can, it's kind of like a class, but everything is public inside, and this works in C as well as C++. So now I can define members. I can define an integer X. I can define a double as a Y. I can also use an array of characters as Z. Okay, so this is how I define the structure XYZ. And inside main, I can now declare a local variable. Okay, so I can say struct XYZ. I'll call the local variable, I don't know, I'm trying to think of a name. Let's just call this A. Okay, so A is my local variable, which is of the type struct XYZ. And that's it. That's the whole program. And to access each item in A as a structure, I need to say A.x is 0, A.y is 0.5, and then I can say A.z bracket 0 is lowercase a, and A.z bracket 1 is a null character. Okay, so I'm just defining a fairly short string in this case. And then we get to the line where the return is, put a breakpoint here, and we'll go ahead and take a look at this program. Okay, so we get to debug. And the program should run. There we go. And then we'll run the program. It will stop at the breakpoint. Okay, so now we got something to talk about. Okay, so if I say print A, okay, so this is the easiest one. It will print the entire structure. So you can see how it breaks it up and say, you know, inside A, there's a member called X. It has a value of 0. There's a member called Y. It has a value of 0.5 because it's a double. And then it also has a member called Z, which is an array of 32 characters. The first one is lowercase a. The second one is a null terminator. But because we know the size of the array, it also actually prints the rest of the string here because it understands, you know, how long, how many characters are in that particular array of characters. So this part is hardly surprising. Okay. So the other thing that I can do is to say print the address of A. Okay, where is A in memory? This is where it is. Okay, you can see how the last 4 digits are EBA0. Okay, and now I'm gonna say, where is the first element of A? What do you guys think it is gonna be? I just looked at the beginning of the entire structure. Now I'm asking about where is the first member of the entire structure. Where do you think it is located? Come on, you guys can figure this out. It's going to be the same. Okay, it's just like the beginning of an entire array. It's also the address of the first element of the same array. So when I press the enter key, you can see the types are different because the address of A is the address of a structure, but the address of A.x is the address of an integer. Okay, so the types are different, but when you look at the actual address, they are the same. They are both ending with EBA0. EBA0. All right. So I'm guessing that this is a compiler for a 64-bit architecture. So an integer is 64-bit wide. So if I were to ask the next question, what did I do? Oh, okay, that's not good. I just lost my program. Let me see if it has kept it. No, it didn't keep it. Okay, I'm gonna have to retype this. Okay, so you guys can keep thinking about what I just said. I'm asking about the address of Y. And over here, I just have to say struct xyz. And this time, I'm not even going to bother. Well, I guess I have to initialize it because the compiler has a nasty habit of optimizing local variables out if I don't do anything with the variables. So I'm going to have to do one initialization, but since I'm more concerned about the address, this should be fine. Not 1 byte, okay? It is not going to be 1 byte later. Because an int is 64-bit wide, so how many bytes after? Come on, Daniel, you're on the right track. Alright, so let's repeat the experiment. Where's the first member? Okay, same location. Now I'm asking where's the second member, A.Y. Nope, not 2 bytes. Okay, so let's find out how big is an int first. Okay, there's a size of operator, and it tells us how. Oh, okay, it's a 4-byte thing. Okay, so all right, so it's plus 4. Okay, so if I look at the address of A.Y, okay, it is 8 bytes after. So it's basically wasting 4 bytes, and I can explain why it's wasting 4 bytes. Even though it only needs 4 bytes, it's allocating 8 bytes. Okay, but we also know that y is a double, and how many bytes do we need for a double? I mean, we talked about double a lot. Okay, so how many bits do we have in a double, and how does that translate into number of bytes? 8 bytes or 64 bits. That's right. Okay, and we can confirm that too. So because we can say print size of double. Oh, I cannot type today. Size of double, and it says 8. Okay, which is correct. Okay, so now we say, where's my last thing, a.z, and we can see that a.z is at the location EBC0 as opposed to EB. Okay, let me move this up a little bit so we can see more stuff. So we can see the second element, or the second member of the structure, is at location B8, and the last one is at location C0. So 8 bytes are in between those two. Okay, so okay, what about the size of the structure itself? How many bytes do you think a struct xyz or variable a in main is going to take up? We know that this, even though this only needs 4 bytes, is allocating 8 bytes for it. This takes up 8 bytes, so now we have 16 bytes, right? And then this one takes up 32 bytes. So we have 8 plus 8, which is 16. 16 plus 32 is 48. So if I ask what is the size of A, it says 48 bytes. Okay, that seems pretty doable. So do we have any questions about all of these things that I'm doing in the debugger? So what I'm doing right now is getting a deeper understanding of something that you have already encountered in CISP360, namely structures. But we are taking a closer look in terms of how it is organized in memory so that we can emulate the same thing when we write code in assembly. Are we doing okay so far? Alright. Okay, I'm not seeing any questions. Alright, so I'm going to make the assumption that things are okay at this point. So what we'll do is we're going to take a look at, okay, let's stay on this page. Okay, let's stay on this page just for the time being, because I want to draw a picture, because I can draw pictures now. Okay, it's a blank page, which is fine. I'm going to start a new page on my tablet. I have to wake it up first because it has gone to sleep already. And start a new page. Alright. So what I'm going to do now is I'm going to draw that structure. So struct xyz is defining a template. Oh, it's not displaying anything. Huh. Okay, refresh. Okay, so do it again. Struct xyz. So that structure is defining how we're going to use 48 bytes. This is byte 0, this is byte 47, because 0 to 47, there are 48 locations. So we know the first 8 bytes, okay, are going to use up for it. So byte 0 to byte 7 are used for member X. Byte 8 to byte 15, now these are all decimal numbers, is used for member Y. And then byte 16 to byte 47 is going to be used up by member Z. Okay, so that's how memory is organized for struct xyz. So understanding this, let's go for something that's simpler. So I'm going to write some code in C first, and then we'll translate that into assembly. So we'll look at main.c, And this program doesn't have any subroutine because I don't need to throw subroutines into the mix. But it does have a structure definition. So XYZ is the name of the definition. And this time we're going to go for stdint.h because I want to control the size of my integers. So I'm going to say int8 underscore t is an 8-bit signed integer. This is my x. And in uint 8 underscore ty, and then we have I don't know, we can have another structure. Okay, so we can have struct w. Okay, so this is a different structure, and w can have just two members. Okay, so it has I and j, and they're both signed integers. So in struct xyz, we have struct w as member z. Okay. So the first thing we do is to declare a local variable that is of type xyz. We'll call it a again, and then we'll say a.x is 0, a.y is 5. Oops, forgot about the semicolon. a.z dot I is -2, a.z.j is 3, and return 0. Alright, extra struct in there. Not sure what you're referring to. Which line number are we referring to? Line 14? Nope. When you use struct in C, you actually have to have the name struct as a part of the name of the type. Classes are different in the sense that when you use a class to declare a local variable, you don't need to spell out the name class. But when you're using structs, you do. Yeah, minor differences between C and C++. So we would need a separate struct for char. No, we don't have. I changed the example, so we don't actually have the char array in this case. Z is its own structure now. Okay, so the first thing we want to do is to look at this. Okay, I hope you guys kind of remember this part. Okay, so I'm going to put it on the side, and then we'll draw a picture of what we just saw in the code. So the first thing is a W. Okay, a struct W. It's pretty simple. It only takes up 2 bytes. The first byte, byte 0, is used for member I. Byte 1 is used for member j. And then struct xyz has 3 things in it. The first item is x using byte 0, and then the second one is y, member y, which is an unsigned 8-bit integer, is using up offset 1, and then location 2 and 3 is a struct w. So this is our z, but this structure goes here. So now I can show you the code and the picture side by side, like that. So do we have any questions about the pictorial representation first of what a structure looks like? Now the numbers 0, 1, 2, 3, and 0, 1, they are referring to just offsets. Okay, so 0 offset from the beginning of a struct xyz is member x. Okay, or we can say 2. Okay, an offset of 2 bytes from the beginning of a struct xyz is the member z of that structure, which is the same member z in the code on line 10. So are we doing okay so far? Between just kind of correlating between the picture and the C code. Okay, I'm not seeing any questions. So now the question is, how do we do this in assembly? In other words, I want to do exactly the same thing like what this program is doing, but I want to do it in assembly. How are we going to do that? So I'm going to split the screen. Okay, almost. Can I unsplit? Nope. Okay, I cannot remember. Oh, we can just quit and then do a V split to split vertically. There we go. Alright, so now, on the right pane, we're going to look at main.ttpasm, okay, which is the assembly code corresponding to this. So in assembly code, I do not know of any assembly language that can define structures. So instead of defining a structure like in the C code, we're going to do it in a slightly different way. So the way we do this is to use labels to designate the offset of things. So we first define w underscore I. So this is just my convention. You don't have to use this convention. So w underscore I is basically saying, where can I find member I of struct w as an offset from the beginning of a struct w. So that is, it's just an offset. Okay, it's the first thing in the struct w, so it's the first thing, and it has an offset of 0. W underscore j is where can I find j, what is the offset to member j in the struct w. Now, most of us would go like, oh, it's just 1, okay? I would rather not do that, okay? Instead, I would say wi 1 plus. So this way, if I want to define anything before I don't have to change how j is defined because it's just relative to where I is. And I would define one more thing. What is the size of a struct w? Well, it is where I can find member j plus the size of member j. So now, we have the size of a struct w, and we can do the same thing with xyz. So we have xyz underscore x defined as 0 because it is the first member of the entire structure, and therefore it is at the beginning of the entire structure, and therefore the offset is 0. xyz underscore y is xyz underscore x 1 plus. So this 1, okay, this 1 here is referring to the size of the member x, okay? And then we have xyz underscore z. So now we ask this question, okay? Where can we find it? Well, where we find this is not hard. It is just 1 byte after y. That's the easy part. So, but the more important question is how many bytes is in a struct xyz? Well, we can do one of two things. We can do the counting manually. In other words, we look at a struct w and say, okay, z is a struct w, it has a size of 2, and then we add 1 more byte for y, we add 1 more byte for x. It's going to take up 4 bytes. Okay? So this answer is not wrong, but it is also not very flexible. Because if later on I want to change some of the items, then I have to manually recalculate everything, which is not something that I would like to do. So instead of doing this, I'm going to say, tell me where we can find z first. Okay? This is the offset to get to member z. And now I have to say, we'll just have to add the size of member z. But how big is it? Well, since it's a struct w, the size is w underscore size. So now we know the size of xyz as well. So I'm just gonna take a little short break here and see if people have any questions. No questions? Okay, so I'm gonna finish this entire program and then I'll zip up everything and post it in today's text channel, because I think if you really just kind of go in and understand this particular program, you will start to understand the rest of the concept that we are trying to illustrate in today's lecture. So I'm starting with a no op, just because we're going to run this through the trace analyzer. And we define the main label even though we don't need a jump, but I do want to designate that this is the beginning of the main subroutine. So now we have the question of how do we declare this local variable a? Well, guess what? Same way that we define any local variable, okay? So we basically have to say a is at an offset of 0 from where the stack pointer points to, because it is the only local variable for main. Okay, so this is the easy part. The next part is a little bit harder. Local var size. Okay, how many bytes do we need to allocate for local variables? Now, since we only have one subroutine main, I'm not going to name this label like main local var size because it's unnecessarily long in that case. So we basically say, okay, where do we find A relative to where the stack pointer points to? Okay, that's the label A. And now we ask, how many bytes is A going to use up? Well, it is a struct xyz, so the size of A is xyz underscore size. So this is the number of bytes that we're going to use up on the stack. Now, local var size doesn't change the stack pointer at all. Okay, we're just defining a label, a symbolic name that is only known to the assembler. Okay, when we run the code, the name local var size is not there in RAM anymore. So the first thing we need to do is to do the allocation. Now you might remember this code. Okay, so we LDIA with local var size, and then we subtract that much from the stack pointer. Okay, this is how we allocate for the local variables, well, or local variable singular in this case. And just as I consistently do, this is how I consistently write my code, is to balance the stack right away. And now we can go back into the middle of the code and ask, okay, now how do we get to each member that we want to initialize? Alright, so Daniel has got a question. Let me answer that question before I try to finish the program. Yeah, it's probably a good idea too. Oh, by the way, there's a tricky way to do this. Okay, so we can certainly do it this way. Boring. Okay, so if I want to express boring using an emoticon, that's a boring face. But I can also do this with a more optimal way. It's subtract D from D. Alright? Because if you subtract D from D, what's going to happen to register D? What is the result of register D minus register D? It's always going to be 0. So it's going to do exactly the same thing. So if it is exactly the same thing, why would I want to use subtract DD instead of LDI D0? Because it saves 1 byte. LDI takes up 2 bytes, subtract DD takes only 1 byte. Well, when your memory space only has 256 bytes, saving 1 byte matters. So anyway, they do exactly the same thing. You get to pick however you want to do this. Alright, so now we ask the question, how do we get to x of A? And we try to put a 0 into that location. So most of you, okay, Aiden's typing something. Just have the assembler assemble both to the same sub opcode. Well, they're not exactly the same either, because subdd is going to change the flag register, but LDI D0 does not. So they're not 100% equivalent. So we can't really quite do that. Yeah, so there are minor differences that the difference is not important in this case, but it might be important in other cases. So we cannot interchange those two opcode, unfortunately. Alright, so now we want to implement line 15 of this code. So since we are not really having a whole lot of time, I'm just gonna implement line 15 and line 17 here. So if we want to implement line 15, for those of you who already have a kind of like a visual idea of how things look like on the stack, you can just go like, oh, the stack pointer is pointing to member X of A already. Okay, so we can LDI A0. This is the right hand side, and doing this is already enough to get the job done for line 15. And you would not be wrong if you say that, okay? But this code is, I would say, I would use the word brittle to describe this code, because if I make any changes, like having some additional local variables, or if I change the structure how XYZ is defined, this code can potentially be broken, because how things are organized on the stack would now be different, okay, if I make those changes, okay? Rearranging local variables or rearranging members inside XYZ. So this code is very, very brittle, which is always not a good idea. Alright, well, if this is not a good idea, what am I going to do? So I'm going to LDI B, okay? After all, we define all of these labels for a reason, right? So this is how we're going to use it. So we got XYZ underscore Z, and we put it into, say, register B, okay? But that's just an offset, right? It's just an offset from the structure, from the beginning of a struct X. So that means we have to find out where local variable A is located first. Now that's pretty easy. I still remember from a previous lecture, it's going to look like this. Okay, we LDI, let's pick a different register, C. And we're going to put A, which is the offset from where the stack pointer points to local variable A. We put it into register C. We add the stack pointer to register C. So now register C becomes the address of local variable A. And once we have that, we can add the displacement to member X. Okay, so my bad here is member X. So now we can add the offset to member X of a struct XYZ to the beginning of the entire structure. So C already has the address of the structure itself. B has the offset to member X from the beginning of the structure. So when I add these two, then C becomes the address of member X inside local variable A. So now we can do a ST instruction, like so. Whew. Wow, that is a lot of code. I mean, that seems kind of a lot of stuff, because what in the end what we are doing here is register C is basically really just whatever register D has, the stack pointer, plus whatever label A has, plus whatever XYZ underscore X has. Okay, and I'm gonna make this really clear that we are referring to label A and not register A. Okay, so by the time we get to the store instruction, register C really is just the sum of D, register D, whatever it has at that point, plus the label A, which is defined to be 0, plus the label XYZ underscore X, which is also defined to be 0. Okay, but I don't want to just use register D, because A may not be the first local variable, and X may not be the first member in the structure. Okay, those can change, when I change the C code. So that's why this is not brittle code anymore. Okay, this is now fairly robust, because if I ever want to change the locations or the relative locations of XYZ, the members XYZ inside the structure XYZ, I can just redefine these things, okay, and then the rest of the code would always have the right label definition. Okay, but this code is also not very optimal, because when we look at this particular summation, 2 of the 3 terms are static. When I use the word static, it means they are determined at assembly time. They are not determined at runtime. Register D is determined at runtime, okay? Because it's the content of a register. But the label definitions are determined at assembly time. So that means label A and XYZ underscore X can be added, at the same time, because they're really just static, numbers or values. Okay, that means I instead of just A here, I can now say a xyz underscore x because I can add these two together at assemble time. There's no need to add these at runtime because it's not going to change. So that means register B, the whole thing about register B is not really needed. So I can get the whole thing done and saving two instructions at the same time. All right. So now the question is, so this is corresponding to line 15 in the C code. I'm going to do line 17 too, and that's the end of today's demonstration. So now I look at line 17 and go like, oh, really? Z itself is a structure and we want to access member I of that structure. Well, I mean, if you look at the picture, okay, which is right here, it's not really that difficult to get to member I of member Z of local variable A. It's kind of the same thing. So we are going to use about the same structure of code, LDI A with -2 this time. This is once again just the right hand side, simple stuff. Now we want to deal with the left hand side again. So we're going to load something here. So we are going to load into, we'll keep using register C. No need to change it to anything else. So we will start with A because A is the offset from where the stack pointer points to the beginning of the local variable A. That's what this A is. It is not referring to register A, it is referring to label A. Okay? And this time we want to access which member of A? We want to access Z, member Z of A. So we have xyz underscore Z. But we also know that xyz underscore Z is a structure on its own, and we want to access member I of that particular structure. So we ask, okay, what is the offset of member I from the beginning of that particular structure, which is a struct W this time? It is designated by this label. So we just have to add all of these things together, but we have to use 2 plus this time. The reason why we have to use 2 plus is because the first plus is going to add up these two items and form another value, and then the second plus is going to add label A with whatever these two terms turn out to be, the sum of those two terms. So we need 2 pluses here. This is where reverse Polish notation looks kind of funny because, well, there are different ways to do this too. You can move the other plus to this place here. That works as well. So if I put a plus here and then remove 1 plus at the very end, that works too. Okay, so it's kind of your choice to do it one way or the other. The rest, easy stuff. Okay, because now C is the offset from the where the stack pointer points to exactly what I need to access, which is member I of member Z of local variable A. So I just need to add the stack pointer to C, which already has the right offset, and now I can store the right hand side to the left hand side, okay, or the location pointed to by register C in this case. So this accomplishes line 17. Okay, and the rest of the program is really just cleaning up the stack pointer and getting to a halt instruction so that we can basically pause the program. Okay. All right. So I am going to keep recording, but if you need to peel off, that's fine with me, because I just want to run this code through the assembler and then get to the trace analyzer just to make sure that everything is good before I upload everything in today's text channel. So if you need to peel off, get your dinner, do your homework for Thursday, go ahead. Okay, it is not a problem. But if you want to stay behind and just kind of watch this whole thing, how it's gonna play out, that's fine too, and you can keep asking questions if you want to. Alright, so this is all done. We're gonna exit the editor. Okay, we cat main.ttpasm to xclib cell clip. It just puts the whole file into the clipboard so I can paste it into the assembler, which needs to wake up. Oh, almost everybody is staying here. Cool. Alright, so I'm gonna highlight the entire column A, delete, and then paste my code here. And then just to make sure that I don't have any typos or stupid mistakes, which happens fairly often. Okay, but not this time. And then we get to RAM file. And just checking, making sure everything looks good. And then we go to File, Download, CSV. And then we'll save this to the temp folder. We'll call this main.csv. So everything is main today. There we go. So now we switch back to the command line interface. And then we'll go ahead and run the program using the command line. So I'm going to cheat again to look for the command line from previous times. Okay, this one looks good. So I'm just going to modify a few things here. So this is main, and this is main as well. The rest I can just keep. So I'm going to run the code. Everything is done. We go to the trace analyzer, and then we go through the whole exercise to reload the content into sheet 1. So this is kind of the raw trace, where it is really kind of difficult for a human to interpret. And that's the whole reason why we have the analysis tab. So we go to import, upload, and then pick up main.tsv. Replace current sheet, use tab as a separator, and do not convert. Okay. This is a pretty short trace, so it shouldn't take too much time to finish processing. Alright, all done. So we go to analysis, and the way we track or we check whether this program works or not, first thing first, okay, we want to make sure register D is going to get back to 0. So we first look at this. We know that there are 77 rows to this particular trace. So we know that we can now jump to row 77-ish and make sure that register D is getting back to 0. It's all good. So the next thing we need to do is to do some manual work just to see what the stack should look like. Okay. So what the stack should look like at this point, this is our stack, right? And then we have only one single local variable. So this entire thing is local variable A. But local variable A is a structure. The first thing in this is X. The second thing in it is Y. The third thing is Z, but Z is broken up into two components. So the first one is Z.I, the second one is Z.J. Okay. We know this location is FF, which is 255 in base 10. This is FE, FD, and this is FC. According to the code, okay, so let's go back to the code first. And I'm going to display both the C code and also the assembly code side by side again. Okay, not side by side, but top down. But all I need to do is to find out what I put into X and what I put into I. So getting back to this picture, we know that a 0 should go into this location, and a -2 should go here. But a -2 is the same as FE in hexadecimal. So this is completely coincidental. I didn't plan it this way. But the content at location FE is FE itself. Okay, so this is kind of what we're looking for. So now knowing what we're looking for, if the program does work correctly, we're expecting to see something like this. Now the other locations are not initialized, but since we reset the processor at the very beginning, so that means all those locations are going to be zeros. So the only thing we can really check is location FE getting updated to a content of FE in hexadecimal. So we go to the trace analyzer, we look at column C, because that would be the only change that we can actually see, which is this one. So that is how we can verify that the program is in fact working. And it has, the C program is now implemented in assembly. In the assembly program is doing exactly what the C program is doing. So that really is the end of today's lecture. I'm going to package up everything, including the pictures that I drew on my tablet, and also the two programs. Well, actually, I'm going to package everything. So there's main.c, main.ttpasm, main.csv, main.tsv, and also the pictures that goes along with everything. So I'm going to pack up everything and then post a zip file in the text channel. So that should help you study, okay? But the important part is for you to go back to look at the C code and look at the assembly code and understand how it works, okay? Every line has a reason of existing, and you have to be able to understand how, why it is important and how it relates to the program, how it relates to the C code. So we got someone typing. Okay, so I'm going to quit this and export from my tablet. Alright, so I need to get they're both main to answer Anita's question. So it's main.c versus main.ttpasm. And I need to go to 310 and I need to export this. Alright, so this is CISP310.pdf. Alright, and you can now zip up everything here. So I'll name the file with today's date, which is 2020-1201.zip, main.c, main.ttpasm, main.csv, main.tsv, and the PDF itself, which is CISP310.pdf, and then I'm uploading it on Discord as not seeing it yet. Oh, it is here. Oh, okay, so let me read the question first. I meant is in general if we need to do that for other pieces of code. Okay, so I'm guessing it has to do with how structures are represented. So the bottom line, if I need to condense this part of the lecture to one single sentence, it's basically this. Okay, the offset to each member in the structure is represented by a label. And let me paste the zip file. And I can't find it here. There we go. Okay. There we go. And I'm not gonna give you guys a new lab today, just because the lab that is due on Thursday can take a little bit of time, because if you don't know how to debug this kind of program, It might take you a little bit of time to get used to the tool, but the whole process of debugging the program that is due on Thursday is by itself a form of studying for this class, because that if your program doesn't work, you need to go in to find out why it is not working. That diagnosis, okay, the reasoning involved in diagnosing a program is one of the best ways to understand the concepts of this class. So I'm not going to give you an additional homework assignment for now, but we'll have one more homework assignment before the end of the semester. All right. So let me just double check to see if anyone has any questions before I stop today's lecture. No one has any questions. All right. So I'm gonna end the lecture now. Stop the screen share and then stop the stream. But I will still be able to answer questions using the text channel. Remember the interrupt thing? I'm gonna have the notification turned on. Yep. All right. So have a good night, and I'll see you guys on Thursday. There we go.